You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. The purpose of this episode is to establish a clear foundation for cloud concepts and architectural terminology. Precise language matters in cloud security because so many decisions hinge on understanding shared meaning. If two professionals use the same term differently, errors can spread into design, governance, and operations. For CCSP preparation, these definitions are more than vocabulary drills. They anchor reasoning across all domains of the exam. They also mirror real-world practice, where contracts, audits, and technical decisions depend on unambiguous understanding. This glossary deep dive ensures you can recall terms quickly and apply them consistently. When you encounter exam questions, being fluent in the language of cloud computing prevents hesitation and strengthens confidence. More importantly, in professional practice, it enables collaboration and clarity across teams and organizations. Cloud computing is formally defined by the National Institute of Standards and Technology, often abbreviated as NIST. Their definition describes a model for enabling convenient, on-demand network access to a shared pool of configurable resources, things like networks, servers, storage, applications, and services that can be rapidly provisioned and released with minimal management effort. This definition sets the baseline for discussions of cloud. It emphasizes elasticity, shared access, and convenience as distinguishing characteristics. By grounding understanding in the NIST framework, professionals avoid drifting into overly broad or marketing-driven definitions. For the CCSP, this standard ensures you frame concepts according to a widely accepted reference point, which is also the foundation for exam content. On-demand self-service is one of the 5 essential characteristics identified by NIST. It means that a user can provision resources, such as storage or computing power, without human interaction with the provider. Think of it as ordering electricity by flipping a switch. You do not call the power company each time you need more. In the cloud, this ability to self-provision resources empowers agility but also demands governance. Without oversight, costs and risks can escalate as users spin up resources freely. For exam purposes, recognizing on-demand self-service reminds you that the consumer holds significant power in cloud environments, which must be managed through policies, monitoring, and controls. Broad network access describes how cloud capabilities are delivered through standard network mechanisms, typically the Internet. This characteristic ensures that services can be accessed from diverse devices, laptops, tablets, phones, using familiar protocols like HTTP. The ubiquity of access is both a strength and a risk. It supports remote work and global collaboration, but also expands the attack surface. For CCSP learners, this term underscores that cloud is inherently networked, making controls like encryption in transit, identity management, and secure endpoints essential. Broad network access connects architecture with security, showing that availability must always be paired with protection. Resource pooling is the foundation of the multi-tenant model. Providers allocate computing resources dynamically, serving multiple customers from the same infrastructure while isolating their environments logically. Location independence means consumers often do not know or control the exact physical location of their resources. This efficiency underpins the cost model of cloud, but also introduces risks: noisy neighbors, potential data leakage, and jurisdictional uncertainty. For professionals, resource pooling requires trust in provider isolation mechanisms and careful attention to contractual and compliance requirements. On the exam, resource pooling signals scenarios where multi-tenancy influences both technical and governance decisions. Rapid elasticity captures the illusion that cloud resources are limitless from the consumer perspective. Workloads can scale up or down dynamically, responding to demand in near real time. For example, An e-commerce site can automatically add servers during a holiday surge, then release them afterward. This elasticity is a key business benefit, but it also requires security controls that scale as well. Identity, logging, and monitoring systems must expand and contract alongside workloads. For exam readiness, rapid elasticity reminds you to think about both opportunity and challenge. The promise of scalability comes with the responsibility to design controls that keep pace. Measured service means that cloud usage is metered and monitored, providing transparency for both the provider and consumer. Just as utilities measure electricity or water, cloud providers track resource consumption for billing, optimization, and accountability. This characteristic creates opportunities for cost management and auditing, but also requires trust in accurate metering. For security professionals, measured service also supports governance, since usage data can reveal anomalies, misuse, or inefficiencies. In exam questions, measured service often signals scenarios where cost, accountability, or usage visibility is relevant, reminding you that security and financial stewardship are often intertwined. Cloud service providers, or CSPs, are the organizations delivering cloud services. The consumer is the individual or entity using those services. Each role carries responsibilities. Providers secure the underlying infrastructure, while consumers secure their data, applications, and configurations. Recognizing the boundary between these roles is essential for both practice and exam success. Confusion about responsibilities is a frequent cause of breaches in real life. For CCSP candidates, fluency with these roles ensures clarity when reasoning through scenarios that hinge on who is accountable for which controls. The shared responsibility model formalizes these boundaries. It states that providers handle the physical infrastructure and foundational services, while consumers remain responsible for securing what they put into the cloud. The line shifts depending on the service model, IaaS, PaaS, or SaaS, but the principle remains. Misunderstanding this model is a common trap. For example, assuming the provider secures all data is incorrect. Data security remains the consumer's duty. On the exam, applying the shared responsibility model helps eliminate distractors and guides reasoning toward answers that reflect the real-world division of labor. The public cloud model offers services to multiple customers over the internet, owned and operated by the provider. It is cost-effective, scalable, and accessible, making it popular for startups, enterprises, and individuals. Use cases include hosting websites, running applications, or supporting global collaboration tools. However, its openness introduces risks: multi-tenancy, compliance challenges, and reliance on the provider's security posture. In exam terms, public cloud scenarios often highlight trade-offs between agility and control. Recognizing when public cloud is suitable versus when private arrangements are necessary is a key professional judgment. Private cloud, in contrast, is dedicated to a single organization. It may be hosted on-premises or by a provider, but is isolated from other tenants. This model offers greater control, customization, and compliance assurance, making it attractive to organizations with strict regulatory requirements or sensitive workloads. The trade-off is cost and scalability, since the benefits of shared infrastructure are reduced. For CCSP preparation, private cloud scenarios emphasize governance, control, and security alignment with organizational policies. They remind you that while public cloud dominates, private deployments remain relevant for specific needs. Community cloud serves a specific group of organizations with shared concerns, such as healthcare providers or government agencies. Resources are pooled for collective benefit, with governance shared across participants. This model reduces costs compared to private cloud while providing tailored compliance frameworks. The challenge lies in governance. Multiple stakeholders must align policies and responsibilities. For exam questions, Community Cloud highlights scenarios where collaboration across entities drives cloud design, balancing shared benefits against the complexity of joint management. Hybrid cloud combines two or more models, public, private, or community-linked, to enable interoperability. This allows organizations to balance scalability with control, using public cloud for elastic workloads while keeping sensitive data in private environments. The complexity lies in integration, ensuring security policies, identity management, and monitoring span across boundaries. For CCSP learners, hybrid cloud scenarios often test whether you recognize the governance and interoperability challenges. It is not just about combining environments but ensuring they function cohesively with consistent protections. Cloud service models provide another dimension of classification: infrastructure as a service, IaaS, platform as a service, PaaS, and software as a service, SaaS. These represent layers of abstraction, from raw infrastructure to complete applications. The further up the stack you go, the more responsibility shifts from consumer to provider. Recognizing these layers is essential for applying the shared responsibility model. Exam scenarios often hinge on identifying which responsibilities remain with the consumer in each service model. This framework organizes the cloud landscape into manageable categories that guide reasoning across both practice and the exam. Infrastructure as a service, or IaaS, provides raw computing resources, virtual machines, storage, and networks on demand. Consumers control operating systems, applications, and data, while the provider manages the underlying hardware and virtualization. This flexibility is powerful but places significant responsibility on the consumer for configuration, patching, and securing workloads. IaaS is often used for migrations or building custom environments. For exam purposes, IaaS scenarios highlight consumer duties in securing operating systems, applications, and data, while reminding you that physical infrastructure remains the provider's domain. Platform as a service, or PaaS, raises the level of abstraction. It provides an environment where developers can build and deploy applications without managing the underlying infrastructure. The provider handles servers, operating systems, and middleware, while the consumer focuses on code and data. This model accelerates development but can obscure some security controls, requiring trust and provider safeguards. For CCSP study, PaaS scenarios emphasize application-level responsibilities, data protection, and alignment with governance. The principle is that providers handle more, but consumers remain responsible for what they create and store on the platform. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Software as a service, or SaaS, sits at the top of the service model stack. In this model, the provider delivers complete applications to the consumer over the internet, such as email platforms, collaboration suites, or customer relationship management systems. Consumers do not manage infrastructure, operating systems, or application code. They simply configure settings and use the software. Responsibilities for the consumer focus on account management, access control, and data protection within the application. SaaS offers simplicity and scalability, but the trade-off is reduced customization and reliance on provider security. For exam purposes, SaaS scenarios remind you that while operational burdens are lightened, consumer responsibility for data governance and identity protection remains significant. Multi-tenancy is a defining feature of many cloud services, where multiple customers share the same underlying infrastructure while remaining logically isolated. This efficiency allows providers to serve many consumers at scale, but it raises concerns about data leakage, performance impact, and noisy neighbor risks. Isolation mechanisms, such as virtualization, container separation, and strong identity boundaries, protect tenants from one another. For professionals, trust in these mechanisms is critical, reinforced by provider assurances, independent audits, and compliance certifications. On the exam, multi-tenancy questions often emphasize risk awareness and the need for contractual and technical safeguards to ensure proper isolation. Virtualization underpins much of cloud computing. It is the abstraction of hardware resources into virtual machines managed by a hypervisor. Hypervisors come in two types: Type 1, or bare metal, which runs directly on hardware, and Type 2, or hosted, which runs on top of an operating system. Type 1 hypervisors are more common in enterprise cloud due to performance and isolation strength. Security considerations include patching hypervisors, monitoring for escape vulnerabilities, and managing virtual machine sprawl. Virtualization provides flexibility, but it also expands the attack surface if controls are not maintained. In CCSP contexts, understanding hypervisor security is essential for evaluating infrastructure risks. Containerization extends virtualization to the process level, isolating applications in lightweight, portable units that share the host operating system kernel. Containers, such as those orchestrated by Kubernetes, start quickly and scale efficiently. They differ from virtual machines by offering less overhead, but also a smaller isolation boundary. Security risks include container escape, misconfigured orchestration policies, and untrusted images. Comparing containers to virtual machines is important. VMs offer stronger isolation at the cost of heavier resource use, while containers emphasize speed and density. For the exam, containerization concepts highlight modern cloud-native architectures and their unique security implications. Serverless computing, often delivered as function as a service or FaaS, abstracts infrastructure entirely. Consumers provide code in small functions, and the provider executes them in response to triggers. This model eliminates the need to manage servers or operating systems, focusing entirely on business logic. Costs are tied to execution time and usage, making it efficient for event-driven workloads. The trade-off is less visibility into the underlying environment and reliance on provider controls. Security responsibilities for consumers remain around code quality, data handling, and access management. In CCSP scenarios, serverless computing illustrates the far edge of abstraction, where convenience is high but shared responsibility remains in force. Geographic constructs like regions, availability zones, and fault domains organize cloud resilience. A region is a broad geographic area, such as a country or multi-country cluster containing multiple availability zones. Availability zones are isolated data centers within a region designed to fail independently. Fault domains are subdivisions within zones, further isolating workloads from shared points of failure. These constructs support redundancy and disaster recovery strategies. For exam purposes, understanding how to distribute workloads across zones and regions ensures availability and resilience. In practice, this knowledge also informs compliance, since data residency rules often tie directly to regional placement. Control plane and data plane separation is a key architectural principle in cloud. The control plane manages configurations, policies, and orchestration, while the data plane handles actual traffic and workload execution. For example, in networking, the control plane sets routes while the data plane moves packets. Security for the control plane is critical, since compromise there means compromise everywhere. Consumers often interact heavily with the control plane through APIs and dashboards, making authentication and authorization paramount. Exam items that reference planes often test whether you understand the different protections required for each. Virtual private clouds, or VPCs, provide logical isolation of resources within a provider's larger infrastructure. Within a VPCs, subnets further segment networks for security and management. For instance, public-facing servers might reside in one subnet, while sensitive databases sit in private subnets. Access controls, routing, and monitoring reinforce boundaries. This structure mimics traditional on-premises networking while benefiting from cloud scalability. On the exam, VPC concepts highlight the need for deliberate segmentation, ensuring that workloads are protected by layered defenses rather than existing in flat, vulnerable networks. Network connectivity models expand on this segmentation. Peering connects VPCs directly, enabling low-latency communication. Transit models centralize traffic routing through hubs, simplifying management in multi-VPC or multi-cloud environments. Software-defined networking adds programmability, enabling policies and routing to be updated dynamically. Each model carries trade-offs in performance, cost, and complexity. For CCSP learners, connectivity models emphasize the importance of governance and security when designing architectures that span multiple networks or providers. The key is balancing efficiency with control, ensuring that convenience does not undermine isolation. Content delivery networks, or CDNs, bring data closer to users by caching content at distributed edge nodes. This reduces latency, improves performance, and enhances resilience against surges. Paired with edge computing, where processing is performed near the user, CDNs reflect the growing decentralization of computing power. Security implications include managing cache consistency, protecting data at the edge, and integrating distributed controls. For the exam, CDNs and edge computing represent practical tools for performance and availability, often appearing in scenarios about global applications or latency-sensitive workloads. Infrastructure as Code, or IAC, codifies infrastructure definitions into scripts and templates. This allows repeatable, automated builds of environments, reducing human error and enabling consistency. Immutability is often paired with IAC, meaning that resources are replaced rather than modified, preventing configuration drift. For security professionals, IAC provides traceability and enforceable standards, but also creates risks if code repositories are not secured. Exam references to IAC emphasize automation, consistency, and governance, showing how cloud architectures benefit from treating infrastructure with the same discipline as application code. Policy as code extends this principle into governance. Policies, such as who may access resources or how data must be encrypted, are codified and automatically enforced by the system. Guardrails prevent configurations that violate compliance or security rules from being deployed. This ensures scalability of governance, as policies apply consistently across thousands of resources without manual intervention. For CCSP candidates, policy as code reflects the intersection of security and automation, showing how governance can keep pace with cloud agility. Exam questions may test whether you recognize this automation as a safeguard, not just a convenience. Identity federation and single sign-on, or SSO, provide mechanisms for trust across domains. Federation allows users from one identity system to access resources in another without maintaining separate credentials. SSO simplifies user experience by enabling one set of credentials to access multiple applications. Together, these reduce password sprawl, improve compliance, and centralize control. However, they also create risks if the central identity provider is compromised. For exam purposes, Federation and SSO highlight the balance between convenience and security, and the importance of strong authentication and monitoring at the identity layer. Observability in cloud-native systems relies on three pillars: metrics, logs, and traces. Metrics provide quantitative indicators, such as CPU utilization. Logs capture detailed events and messages, offering forensic and diagnostic value. Traces show the flow of requests through distributed systems, illuminating dependencies and bottlenecks. Together, these pillars provide visibility essential for monitoring and incident response. For CCSP learners, observability reminds you that security is not just about prevention, but also about detection and recovery. Exam items often test whether you understand the role of visibility in maintaining secure operations. Resiliency patterns ensure that cloud systems withstand failure gracefully. Redundancy means duplicating components so one can replace another. Failover ensures that when one service fails, another takes over automatically. Graceful degradation means systems reduce functionality rather than collapse entirely under strain. These patterns reflect the reality that failure is inevitable, but catastrophe is not. Designing with resiliency in mind is a hallmark of professional cloud architecture. For the exam, recognizing resiliency strategies ensures you select answers that emphasize continuity, recovery, and user trust. In summary, Mastering cloud terminology builds the foundation for accurate reasoning about architectures and responsibilities. Terms like elasticity, federation, or observability are not just jargon. They are anchors that shape decisions in design, governance, and operations. For the CCSP, fluency in this vocabulary allows you to interpret exam questions precisely and respond with clarity. In practice, it ensures collaboration across teams and confidence in decisions that affect organizations and customers alike. Precise terminology is the shared language that makes secure, resilient cloud adoption possible. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.